Okay, so we now look at one more lecture concerning stochastic dynamics, and then we sort of wrap up all the discussion we had on this part of the problem. So remember, our last steps in the course were that of essentially renormalizing the Schrödinger equation, the Fokker-Planck equation, to achieve an effective theory formulated only in terms of microstates. So after reducing the dynamics to a discrete jumps to energy basins, essentially, then your highly multidimensional, horrible dynamics in, say, typically 3,000 or 10,000 of dimensions is actually mapped onto a simple network with a bunch of states, a discrete set of states. Well, depending on the system, you might, and depending on the resolution you want to achieve, you might have a considerably large number of states. What is the parameter that determines how many states you have in the system? Well, essentially, where you choose to set your cutoff to develop an effective theory. In other words, remember, we might have, in the ideal case in which the spectrum contains many gaps, such as in this case. Now there is a very quick transition between these basins, suppose KT psi 8, a small scale. Relatively slower transition between these states, and then extremely slow transition across this. So if I were to, then if I assume that here the potential goes up and goes up here too, if I were sort of imagining how the spectrum of the Fokker-Planck operator looks like for a system like this, I would imagine it has a ground state, which is exactly 0. It has one extremely slow global thermalization scale, which is dominated by a single barrier here. Then somewhere up in the spectrum, at a scale which is proportional to the exponent of this barrier, I will have a bunch of states, approximately one for each of these basins. 1, 2, 3, 4, maybe 5, 6, 7, 8, and 9. I don't know. So suppose there are 9 of such states here. And then much up in the spectrum, I have a bunch of very fast processes which are associated between transitions here. Now, you might choose to set your cutoff here. Well, if you do that, or even above, say above here, well, much above this, basically, you're only neglecting out the microscopic transition within any of these states, but you're keeping all of these basins here. So you have as many states as energy minima you see in this picture. And your network will be very large. Or you might say, I'm not interested in resolving this fast local dynamics because maybe my resolution power in experiment is much lower than that, or maybe because I'm interested in processes that are completely uninfluenced by that. Who knows? It could be theoretical, biological, or experimental reasons. Then you might consider a lower cutoff, in which case I'm not resolving this dynamics. So basically what I'm saying, I'm replacing all this with one single state. This is another state, this is another state, another state, another state. This is not even a state. Well, this probably is one state, and this is one state. I don't know. You see what I mean? And then you have a smaller network, and in each network, so basically, this is my larger network. drawn on a plane, one of the advantages of mapping continuum to discrete dynamics is that you can actually draw it on a plane, even if the underlying dynamics is very high dimensional. Then you might discover that all these states are fast interconnected because they are not separated by any energy barrier. So they represent this macro state here, if you lower the cutoff. And then you may discover that all these states are very fast interconnected, and there are rate limiting steps between some of these states. So in the end, these are associated to one state, to one state, and to one state. And these are the yellow states here. Eventually, you might discover that some of these states are interconnected on an even lower scale, lambda. These states here, maybe they are these states here in this plot, are all fast interconnecting relative to the time it takes to go from this set of states to this set of states. So at extremely low resolution, you have a two-state system represented just by two states with the corresponding matrix. In principle, you can use the renormalization group methods and equations to systematically identify which states should be grouped into larger macro states and computing the rates between the microstates using renormalization group methods. And actually, this was the thesis of a student of mine. You can look up in the papers Orioli and Faccioli, and I think it's 2016 or 2017, I don't know, a couple of years ago. And you will find all the mathematics that we use to perform this rigorous mapping and discover effective theories and identify which states, given a very fine-grained descriptions, a macro state model with many states, how do you go to lower the cutoff and get, I'm using capital letter to represent the effective theory, a rate equation for macro states. So finding the macro states as a function of microstates and finding the effective kinetic rate by means of the information you have in the microscopic kinetic rates. It turns out you can do that in a formal and rigorous way. I'm pretty proud of this paper, to be honest with you. It was a kind of a mathematical tour de force to figure out how to do that. But it was quite successful, and if you read the paper, you see. I'll probably put it on the Telegram page how you can possibly do that. Of course, everything that I put on the Telegram page, which is not strictly related to, I'm not expecting you to read nor to understand it. It's just that somebody's particularly interested, you can find the references there. Okay, but now we want to address the fundamental question: is how do we find a microstate? Or define the microstates. In first place, well, you might say, well, easy. I diagonalize the Fokker-Planck operator, and then I look at the Boltzmann distribution, which is the ground state. This is the Boltzmann distribution, maybe. And then everywhere I see something that looks locally like a Gaussian, I identify that with a state, which is the analog of looking at the energy basin and say, anywhere I see a basin, that's my state. And then I build in a combination between the states, and then I say put particles here, and I count how many times per unit time I see a transition to here, how many times I see a transition here, and I get my first K1, 2, and K2, 1 metrics. Then I sit here, I run molecular dynamic simulations, until I see a transition, and I do this many, many times, and I get the K23, K32, and so on and so forth. I construct the matrix, and once I've done all this, I can forget the underlying dynamics and only use the network. Well, this is in principle correct, and in practice totally useless. Why? Well, first of all, if you are in 1D, you can plot and the potential and look at the potential and look where the potential has minima and do exactly what I just discussed. If you're in 2D, you can do the same. Basically, you would a density heat map plot, and you look at the high density. You look at a two-dimensional contour plot or whatever, and you can still get the same information. The problem is that we're dealing with complex systems with typically a few thousand dimensions or more, maybe 100,000 dimensions. And if I give you an energy function of 100,000 variables, maybe describing the interaction of all the atoms in a molecule, I bet you are not able to guess all the energy basins. First of all, there is an exponential number one. Second of all, some of them are totally irrelevant, they're never visited. And then even you cannot find them. Already finding the basin. Well, if you could find a global minimum of potential energy of a protein, you would be able to predict the native state given the force field. And this is the solution of a protein folding sequence structure relationship, which would worth a Nobel Prize for sure. So the problem here that we're beginning to face, and is one of the problems that I listed as a keyword or in this course at the beginning, introductory lecture, and is the curse of dimensionality. And by curse of dimensionality, I mean things that are completely trivial or at least feasible in very few dimensions become exponentially hard with a number of dimensions and very soon unfeasible. You may say, I don't need to know the potential energy, For instance, I can shoot many, many, many long trajectories from different points, saving configurations every so often. And then after I've done that, I have generated clouds of points in configuration space. Some points are scattered, some points are more dense around regions. And then I look at where the density of points is larger, and those are my microstate. And I'm using the dynamics to find them rather than just me looking at the potential energy function. True, but wrong. What do I mean by this? It is true that in principle, if I do this on a plane, once again, I can divide my plane on a mesh, on a grid, shoot many molecular dynamics trajectory, and then wait very, very long until I've become ergodic, and then count how many times I found particles in each point of the grid to reconstruct the Boltzmann distribution without having to read it off the potential. Maybe you can do this for 3 dimensions. But this kind of approach becomes exponentially hard with a number of dimensions. In other words, there's a problem here. First of all, the number of points that you need to, the grid, the number of lattice cells you need to characterize the system grows exponentially with the number of dimensions, which means that you need an enormous amount of statistics to populate this plane in configuration space. So there's one feature of complex systems and in general high dimensional systems which is beginning to emerge from this discussion. And it's the following. In high-dimensional system, you are never, ever, ever ergodic in any sense, meaning the best you can actually produce in a finite simulation time is just a very extremely sparse, scattered set of points in a huge dimensional space. You can already understand why this is the case. Think about your two boats that want to cross a canal in Venice before the COVID made those canals completely empty. Well, of course, suppose there's only one room for one boat. Well, when they approach, you're jammed and have to backtrack and then find a way to sort of sneak in through. So it's very easy to fill up the configuration space in 2 dimensions in Venice. Now suppose you're flying. Well, already you can fly on top of each other without no problem whatsoever. Configuration space grows enormously in 3D with respect to 2D. Right? Now if you do this to 3,000, 300,000 D, points are effectively all distance from one another in some sense. You never really get many points to be very close to the same configurations because there's so many options, so many dimensions. So, while all the concepts that we have worked out are quite rigorous and formally well defined from the theoretical point of view, as you really go into large dimensional configuration space, the question arises whether they are practical or not, whether it is possible to make use of them in practical simulations. Now, all this discussion clearly rises up the urge for a preliminary step that is used to identify dynamics in complex space and try to map it onto a network. And that's called dimensional reduction. What is dimensional reduction? Dimensional reduction is kind of sort of a mathematical procedure through which you get rid of unnecessary dimensions and only retain the relevant manifold in a large dimensional configuration space. To give an example, let me consider dynamics suppose we have a dynamics in a 2-dimensional configuration space, but suppose the potential energy is extremely steep and high, except onto very, very, very narrow region, something like maybe here, something like this. So you can think about this to be a river in a valley, right? In the Grand Canyon. So if you were to simulate Langevin trajectory starting here, all you would probably see is something like because anytime the particle tries to climb the wall, it finds a huge energy barrier. And therefore, anytime the particle, say, attempts to be here, there's a gradient term in the Langevin equation that would push it back. So this system is 2-dimensional, but if I look at it, there is a highly non-linear 1-dimensional manifold which effectively describes the entire dynamics. Well, it's a non-trivial manifold. You see the shape is highly non-trivial. So if I were to look at the data that I've generated through a simulation, they would look like this. Now, if I were to if I'm good enough somehow to be able to identify this effective one-dimensional manifold in the two-dimensional plane, I would have achieved an important simplification by reducing by half the number of dimensions of my system. Well, in this case, this is not particularly useful because I can do things in 2D anyway. But clearly, if I go to a realistic system where I have maybe 3,000 dimensions and I can bring them down to, say, 10, then I get an exponential gain, and the power of the exponent would be just gigantic. So basically, there's no way I can do things here. No way. And maybe there's hope here. So I would like to group configurations in such a way that I can sort of lower the number of dimensions. And here, dimension reduction is a huge, as you can begin to understand, is a huge business, both in molecular simulation, but in general in data science. Because this is, with all respects, a big data problem. At least some features of the big data. Dimensionality is too large, the data set is too large to extract from it any information. We need to be able, in an unsupervised, possibly way, to filter out relevant, meaningful information from gigantic data sets, which, if I just look at them as raw data, are not interpretable by human eyes at all. So how can I do that? Well, there are basically two main steps that are being used in practical algorithms to do this. And they are taken in order. One step is called featurization. And the second step is the actual dimensional reduction. Or, in general, as a prescription to find a marker state. Well, here it really depends on what kind of approaches you're taking there. In a sense, this is basically science being developed, starting since, say, 10 years ago. So, as you can imagine, when science is at the frontier, many different approaches are being developed in parallel, and some of them have analogies, some others are completely different, and it's very difficult in a lecture to tell you this is the way to go, because there's no unanimous consensus what is the best way to go, and every group has its own strategy. I'm trying here to sort of steal out the main ideas that are behind it, and then in the notes you find some application, but in general the literature is the place to look at the moment, because once again this is science being developed rather than being synthesized and understood and distilled like other fields of physics and statistics are. So what is featurization? Featurization is the idea that maybe at the lower level of discussion, all the observables I'm interested in, let me call it O, which is in principle a dynamical observable, depend on x of t, not through all the 3n configuration, but essentially through a limited number of collective variables. And maybe there is the smallest possible set of collective variables that enables me to saturate this equality very well and then if I can find it, then I don't really need to represent the systems in terms of my 3n collective microscopic variables. All I need is the coordinates in this plane in this manifold selected by this n effective collective variables. So basically I've built a nonlinear map between, say, the configuration space and this is nonlinear, meaning that R1 is not a linear combination of the x's, is whatever function it is. Linear. So we would like to find these coordinates, obviously. So the question that I really would like to address with you today is, can we identify the ideal definition of the collective variables? What I mean is, can we identify the best possible collective variables for any system that have the probability of saturating the observables somehow, given some assumptions? Well, at least defining them is a good starting point. Maybe we are not able to compute them exactly, then we have to work hard or make assumptions to approximate them, but at least having an idea what are the most general properties we would like for these collective variables to featureize the system look like. And in order to do that, I'd like to introduce a new concept, that is the concept of kinetic distance. Now, to illustrate the concept of kinetic distance is something that tells us when two configurations belong to the same states or not. Well, clearly, if we can define a metric, a norm, that allows some kind of metric dk, which depends on two configurations, such that when this matrix is closed, then these two configurations are in the same basin. And when this matrix is large, when this configuration are in different basins, then this would carry very valuable information for the problem of dimensional reduction that I was referring to. And maybe, based on this information, I can sort of have a guidance to understand what is the best featurization. Okay, so what would be the best metric possible? Well, one possibility is structural distance. For instance, if this is a Euclidean space, this could be the Euclidean distance between the points. But that's obviously a very bad choice, right? Because, say, consider these 2 points here. Or maybe this, let's look at the landscape let's look at the landscape maybe like this. Consider like this, point 1, point 2, and point 3. Now, clearly, point 1 and point 2 belong to the same state, while point 2 and point 3 belong to different states. However, according to the Euclidean distance, point 2 and point 3 are closer than point 2 and point 1, because there is a barrier between 2 and 3. Okay. So the question is, can we can we actually define some kind of metric that takes into account of the facility through which facility means so completely different meaning in Italian than in English. This is really a false friend. What I mean, the effectiveness, the rapidity through which two configurations diffuse into one another and then use this as a definition of metrics. You see, because these two configurations are in the same state, because basically you can diffuse to one another within a short time scales, and if you want to go from here to there, you really have to cross a barrier before you can diffuse from 2 to 3. That's the real difference from the kinetic point of view. So what you can do is to define a family of metrics depending on the cutoff parameter of your effective theory, called the kinetic distance. So given a timescale tau, you can define the kinetic distance in the following way. Let's see if this makes sense to you. Now, and sorry, I'm missing a term. Now, what this expression is giving me, this is a conditional probability, the usual Fokker-Planck conditional probability. And to diffuse from point x2 to some point y, and this is the probability to diffuse from x1 to the same point xy, integrated over y, in a time tau. Now, if you are within the same basin, maybe there's another state here, but if x1 and x2 are 2 points in the same basis, and tau is chosen slightly longer than the normalization time within these small bases, then clearly this distribution will converge within the time tau to the same Boltzmann distribution.